So pick up from where we left over, which are concepts of like Gibbs equations and the relationship between those partial derivatives and also the state functions and measurable coefficients. So today we want to move a little bit away from equilibrium. So whatever we discussed before are talking about Gibbs equations in closed system, only reversible processes, and PV work only. So just refresh your memory on the term reversible. When we're saying a process is reversible, what we're saying is that system is always infinitesimally close to equilibrium. And any infinitesimal change will push that system back to equilibrium. All right, so if you look at infinite time, when we're talking about reversible process, you can still have reactions taking place, but it's just taking place at a very, very slow rate. But that's not the reality, right? We don't live in a world where only reversible processes taking place. So what about non-irreversible, what am I saying? What about irreversible processes that's not like super, super slow, like a real chemical reaction? How do we describe processes that taking place irreversibly? So we'll get started by introducing the terms or introducing the concept of chemical potential. So here's the way leading to the definition of chemical potential. We'll go really slow here, so let me know if you have any questions. So some of the things we'll start. Let's look at our Gibbs equations, right? So when we're talking about these Gibbs equations, let's start simple with only one phase system, that is in thermal and mechanical equilibrium. So in thermal and mechanical equilibrium, what we have is your temperature and pressure are well defined at thermal and mechanical equilibrium. But now this system is not at material equilibrium. It's also pretty straightforward to understand. You can have a chemical reaction taking place in a water bath of constant temperature and your atmosphere pressure, right? So it's something that's easily achieved. Now, if we think about it, then our Gibbs free energy will become a function of temperature, pressure, a number of moles of all kinds of chemical involved in that chemical process. All right, so here when we say N1, N2, all the way to Nk, we're saying that's the number of mole of all your reactant and product involved in the process. So, based on our calculus knowledge, we can write it out for infinitesimal changes. Or if we write the total differential of the Gibbs free energy, what do we have? Well, we have the partial derivative of G over T at constant P, Ni dt. So this Ni, subscription I, just say like, okay, that's all the way, that's every reactant or product involved in the process. Plus partial derivative of G over P at constant T, constant Ni, and dP. And at the end, we have this term. Now we're taking consideration of the partial derivative of G over Ni. Now here, we start from 1 and all the way to K, right? So we're talking about N1, N2, N3, all the way to Nk. And everything, including like temperature, pressure, and every other number of mole of substance are kept unchanged in this process. And we sum that term together using that summation symbol. And then we have a little bit more information. Now, in this case, we have dG equals to negative S dt plus VdP for reversible processes. Now, in this setup, remember we're saying our system is in thermal and mechanical equilibrium. So these first two terms are in equilibrium with each other. So if we're only considering the first two terms here, we have these using our Gibbs equation. We have that first partial derivative equals to negative s, and our second partial derivative, dg over dp of t and I equals to v. All right, so the reason we can do it is because we say, hey, we're talking about a system under thermal and mechanical equilibrium. So our new expression for delta G becomes, or dg, becomes negative s dt plus v dp, and plus this term here. And that summation term looks like horrible, but if you think about only like two system, where a two-component system, right? You have reactant A goes to product B, and what this term is just effectively saying we have partial derivative of G over dN1, where T, P, and N2 are kept same, and dN1, plus partial derivative of G over N2, where T, P, and 1 are kept the same for two components. So it looks horrible, but it's just to simplify a little bit. So with this in hand, what we find out is if we want to just focusing on the material equilibrium, where you have either a chemical reaction or a phase change, leaving the thermal and mechanical equilibrium aside, right? We should be just focusing on this last term here. And from here, we thus define a chemical potential. So that's our mu I, and that subscription I is specified that is a chemical potential for that specific substance I. Let's say a like water liquid, then your I is water liquid. Now let's assume we have one phase system. We'll talk about phase change shortly after. So here's the definition of our chemical potential. So your mu I is defined to be the partial derivative of Gibbs free energy over the change of the number of mole of that substance I. So that's the partial derivative of Ni, where we kept everything else constant. And as a result, we can rewrite our Gibbs equation to include chemical potential. All right, so the first part, the negative SDT and VDP, that's our Gibbs relation. We kept the same. And at the end, we add our chemical potential here. So before we move on, let's do one more thing. So now we have the chemical potential added onto your Gibbs equation for your delta, for the expression of your dg. What about other Gibbs equations? So it turns out, like all other Gibbs equation, you can add that chemical potential at the end to take consideration of the material equilibrium. Now let's just do one quick derivation together and see how that works out. Let's again pick our enthalpy as an example. So what we know here, we know that G, by definition, equals to H minus Ts. Or we can write enthalpy equals to G plus Ts. And at the same time, we know that dg equals to minus SDT plus VDP plus the chemical potential. So what that tells us is we can write my dH equals to dg plus TdS plus SDT. All right. And some of the term cancel out. We got TdS plus VDP plus our chemical potential term. All right, and that's the expression we have up there. Let's pause here and see if we have any questions before we move on. Sounds good. And then we talk about chemical potential for just one phase, adding different phases to the system, just adding a little bit more complication to this expression. So now the question becomes, what about we have a system with multiple phases? Again, when we're talking about phases, you're talking about liquid, solid, solution, or gas phase, right? So in this case, let's use the nature of our Gibbs free energy, which is an extensive state function. So it being extensive just means your total Gibbs free energy G would equal to the summation of your Gibbs free energy of every phase alpha. So that gives us this term here, the G with a superscription alpha tells you that's a Gibbs free energy of phase alpha. And again, using calculus, we can write dg equals to, well, the addition of all these dg alpha, right? So this is what we're using is dx plus y equals to dx plus dy. And what we had before. So again, using this term, dg equals to negative SDT plus VDP. Now, when we're talking about, when we're adding that specific phase superscription into this equation, what we can do is add that superscription here. So we're talking about the Gibbs free energy of that specific phase alpha. So for our entropy, we have to define it for our specific phase alpha, and likewise for our volume and our chemical potential. So for every dg alpha, we have that new superscription, just saying now we're just specifically looking at your free energy, your entropy, your volume, your chemical potential in that specific phase alpha. And then we end up having this final relations. So adding it all together, so that's like using this equation and this equation. So adding it all together. When we add all this like S alpha and you add that all alpha up, you get the total entropy. So remember, entropy and your volume, they're all like extensive state functions. You can add them up. And here you have our chemical potentials. And this term here, again, this double summation looks horrible. But if you think about, like, let's look at an example here. Let's imagine we have a two phase that are alpha and beta with two substances. Two substances, X and Y. All right, so what does that double summation gives you is an expression here. So we're summing all alpha and all I with mu I, the chemical potential alpha, and also dni alpha. So for that two-component, two-phase system, what we have is just mu x alpha dnx alpha plus mu y alpha dny alpha plus mu x beta dnx beta plus mu y beta dny beta. So it's just like write everything out. It's going to be a really, really long equation. That's why we use a double summation. But now, what does that double summation mean? It's nothing fancy. It just tells you we add all these terms together. All right? How are we feeling? With me so far? Okay. Let's move on to look at some specific systems. Well, okay, so before we do that, let's just quickly summarize what we went over. So in this process, in this section, we defined or we discussed material equilibrium at constant Tp with our chemical potential. So what does that mean? So when we look at the general expression of delta G with that chemical potential, so now it's like we don't care whether or not we're at equilibrium. This is the general expression for your Gibbs free energy. And in this case, at equilibrium, we have delta G equals to 0, or dG equals to 0 at equilibrium. And since we're talking about a reaction or a process at constant temperature and pressure, now the dT and dP term both equals to 0. So that tells us now when we're talking about a material equilibrium, effectively what we're saying is this chemical potential term equals to 0. All right, and remember when we say material equilibrium, we're talking about two different types of material equilibrium. That includes phase equilibrium and also reaction equilibrium. All right, and before we move on, I just want to finally define our chemical potential again. So in this kind of expression, what we have, this mu is the chemical potential. It is specific for substance I in phase alpha. So now if you have like liquid water, right, then your I here would be H2O, and your alpha here will be liquid L. And your chemical potential is defined to be the partial derivative of your Gibbs free energy in that specific phase over the change of your number of mole of that specific substance in that specific phase, with everything else kept constant. All right, so that's a quick introduction to chemical potential. And then let's look at the two applications of your chemical potential, which is to describe material equilibrium. So we'll first look at phase equilibrium, and then we'll look at equation or reaction equilibrium together. So phase equilibrium. Again, phase equilibrium, we're talking about, we have same chemical space that are in different phases, right? You can have a vaporization of water between from liquid to gas phase. So let's think about equilibrium situation first, or you can imagine a vaporization of water at your normal boiling point. So what do you have here? Using the definition of our chemical potential, we can first write out this expression. So that's the chemical potential, that's the general expression. In this case, we only have one substance, which is water, but we have two different phases that's given by the superscription L and G here. So we only have we only have one component, but two phases. And at equilibrium, this chemical potential term equals to 0. Or the other way to put it is, if we think about it, we can go down here. When we have liquid goes to gas, I'm just gonna say some kind of liquid goes to some kind of gas. Now imagine the number of mole of your water that's being changed, so dN H2O. So that's the change of your number of mole of your H2O going from liquid to gas phase. And in this case, on the left-hand side, you have the dN number of mole of liquid. So this one is going to be a negative number because it is reactant, right? The number of mole of your liquid H2O is decreasing. The negative of your change of liquid water number of mole equals to the change of your gas phase number of mole. And the numeric number will always be the same. Or the other way to put it is when we plug in that dN H2O, we have negative mu H2O liquid dN H2O plus mu H2O gas dN H2O equals to 0. You take that dN H2O out, you get mu H2O gas minus mu H2O liquid times dN H2O equals to 0. And in here, this term here is not 0, right? Because we do have number of moles of your water liquid go from your liquid phase to the solid, to the gas phase. So this dN H2O term is not 0. So that tells us this chemical potential difference must be 0 in the process. Or the other way to put it is we can write mu J in some phase beta equals to mu J in some phase delta. So we have phase equilibrium. So we have phase equilibrium between beta and delta if this term is true. And again, we're talking about a closed system where PV work only and only one substance. Right, so at phase equilibrium, the chemical potential of that mu J beta of phase beta and mu J delta of phase delta, they're equal to each other at phase equilibrium. So what about irreversible phase changes? So likewise, that's considering the vaporization of water. But now the vaporization of water is taking place at let's say like 5,000 K. All right, so once your water is vaporized into gas, the reaction is like irreversible. So how does this term becomes? Again, we have our definition or the expression of your Gibbs free energy, ds. And for our irreversible processes, what we know is that dg is smaller than negative SDT plus PdB for irreversible processes. So we went over that in lecture 9, if you want to go back and review it. And let's do the same kind of analysis we did before, like in the equilibrium phase scenario. What we have is we're talking about this term becomes a negative number because we want the total dg to become negative. Again, we're talking about constant Tp, so these terms doesn't come to play. So in order to have this term to be negative, we must have, well, that's just a write-out expression of your vaporization process, right? You have the liquid, the chemical potential of liquid water, the change or infinitesimal change in number of mole of liquid water, plus the chemical potential of gas phase water, and your change of moles of your gas phase water. This term to become smaller than 0. So for this for this irreversible processes, again, we have our dNH2O equals to negative dNH2O, which is liquid, equals to dNH2O in gas phase. So this one is just saying for this one component, right? We do not destroy our material along the way. So the change of mole of your water in different phases must equal to each other, just with opposite sign. And in this case, we can then rewrite our expression to be mu H2O gas minus mu H2O liquid times dN H2O. And this is going to be smaller than 0. And in this process, we know that our change of mole of your H2O is a positive number. So this term here at the beginning must be a negative number. Yes?
Why is the term positive?
This one, you see our define here. We're talking about the change of number of mole of water. Now we're saying our reactant is always a minus sign in front of it, right? If you think about the change of your number of mole from liquid to gas, it's a reaction it's a vaporization process. So that your liquid water, the number of mole of your liquid water will always be decreasing, while the number of mole of your gas-phase water will always be increasing. Yes?
How come it's not just an absolute value then?
Well, if you want to put it as an absolute value, that's also fine. But this one, we're just saying that's a positive number. Yes?
I guess I'm still confused because wouldn't the change in the amount of like water molecule moles be zero if you're just changing the phases? That's why I'm kind of confused.
Okay, so we have different superscription here. We'll specify the change of number of molecule of water here, not talking about the water is reacting, but talking about the phase of your water molecule is changing. So this superscription tells you that's your water in different phases. All right, and we went over lots of calculations before where you have like substance in different phases, they have different thermodynamic properties. So that's why we want to keep a close track in which phase your water molecule is in. So what does this tell us? This one, we have the mu H2O gas minus the mu H2O liquid to be a negative number. Oh, no, negative. So, what is the take-home message here? The take-home message here is for an irreversible process. Now, this case, we're talking about an irreversible vaporization between liquid water to gas-phase water. What that tells us is when you have a substance J, let's generalize our conclusion here, right? So when we have a substance J, just one substance, that flows instantaneously from one phase to a second phase. So your initial phase will have higher chemical potential than your final phase for that irreversible processes. Now for this general statement, if we're using our example there, what we have, our substance J here is H2O, right? It flows spontaneously from a phase with higher chemical potential. So here our higher chemical potential, you have our delta equals to liquid, to a phase with lower chemical potential, where our beta is our gas phase. So what our derivation show is this one is a irreversible vaporization. I think I made some typo in the annotated note, and I'll fix it later, but if you don't, this one is our updated version. All right, how are we feeling? Now we're talking about irreversible processes. When we're talking about irreversible processes, you're trying to predict how your equilibrium is going to flow, how your reaction is going to go, right? So the reaction always goes from a phase with higher chemical potential to a phase with lower chemical potential. And let's take, yes.
Just a little bit about this. When you're doing, right after the irreversible process outline,
That's fine.
can you just explain how you got the sign errors? I'm kind of confused with what he was asking earlier about why the change in moles of water is positive.
So if you think about it, we're talking about vaporization. So you have a cup of water, right? Let's say at the beginning you have 1 mole of liquid water. You have 0 mole of gas-phase water or water vapor, right? But along the process of this irreversible vaporization, your number of mole of your liquid water is always decreasing, right? It's vaporizing it into water vapor. So at the end, eventually we'll have every molecule of your liquid water transferred into that water vapor. So if we're talking about the difference, right, when we're talking about when we have this D here, we're talking about the change in the number of mole of your liquid water molecule. That's an infinitesimal change. So that's always going to be a negative number.
I understand. I got those two.
Okay.
I was the overall change in number of moles of water.
Well, the overall change is, this one we do not have any subscription, but what we're saying is that's the number of water molecules that moved from one phase to another. We're not suggesting your water is reacting. We're talking about these are the number of mole of water that's moved between one phase to another.
At a certain instant in time?
Yes.
Because overall, it would go from 1 mole to 1 mole?
Yes.
Okay, but it's at a certain instant in time?
Yes.
Okay, I understand. Thank you.
Let's look at one more picture here, and then we'll take more questions. The picture here is, well, again, what exactly is chemical potential? And I hope to make a link between what we just discussed to something you already know. So analogous to heat and temperature. Now, when we're talking about heat, imagine you have like two pieces of metal. One is at higher temperature, one is at lower temperature, right? So spontaneously, you will have heat flow between that piece of material with higher temperature to that piece of material with lower temperature. In this process, you have heat, which is the change of Q, and temperature here is an intensive property, or the flow of heat is governed by temperature change. Likewise, when we're talking about a chemical reaction or a phase change, what we mean is that the flow of substance J from your phase beta to phase delta is governed by chemical potential. All right, so the relative chemical potential differences tells you how that phase change is going to flow. And in this case, our chemical potential is also an intensive property. Right? If you remember when we have that number of mole of change, you have that N in play along with your chemical potential. So your chemical potential here is also an intensive property. All right. I hope this analogous help you understand a little bit more about why do we care about chemical potential and how exactly does it work. And to make it even more general, what we can have is, for example, in a closed system that is in thermodynamic equilibrium, the chemical potential of any given substance is same in every phase in which the substance is present. So as long as you have thermodynamic equilibrium, or that means like all your thermal, mechanical, and material are all in equilibrium with each other, then the chemical potential will all be same. So you do not have these kind of irreversible flow between phase beta to phase delta or vice versa. Okay, any other questions? Yes.
So that last statement, does it make it, so it's saying it is reversible now?
Right, so this one we're talking about thermodynamic equilibrium, right? So at the equilibrium, you only have like reversible or infinitesimal processes going back and forth. Okay? All right, and now let's address the question, like why is this a chemistry class? So let's move on to talk about reaction equilibrium. So in this case, I got so many questions like, why is this class a chemistry class? But nevertheless, let's look at reaction equilibrium. And this is going to link us a little bit back to the chemistry world. Now for chemical reactions, let's look at a typical reaction here. You have A, which is our coefficient, and also our A1, the big A1, that tells you the identity of your reactant A1. And likewise, your on the right-hand side, your small e, that's a coefficient of your product, and the big AM, that tells you that's our product. It's just a notation. You can notate it any way you like. But the take-home message here is for us to have a mathematical representation of chemical reactions, we want to reorganize a little bit so that this chemical equation is easily representable mathematically. So what we're doing here is moving everything to the right. All right, so now we are moving all my reactant to the right-hand side of this arrow. And in moving it, we now have our stoichiometric number, or nu, with a subscription I. So we define our stoichiometric number which is negative for all reactants. So for example, we have mu1 equals to negative A, because A, that's here, that's our negative A. And negative B for our mu2. And et cetera, et cetera. And our nu will be a positive number for products. Right, so you have like mu m equals to E, mu m plus 1 equals to F, right? So this one is our mu m. This one is our mu m plus 1. Or the other way to put it, now we define our stoichiometric number, we can rewrite this like really long expression into this general form. So it's always a reaction goes from nothing to the summation for all reactant end products. We have mu I, AI. Right, so just keep in mind, reactant, the stoichiometric number is negative. That's straightforward enough. And then, now we have our coefficient and the nu I that's defined. Let's look at another term, which is called the extent of reaction. That's called C. And that tells you the proportionality of reactions. Did I get that wrong? I actually don't know how to pronunciate it. I call it C all the time. Yeah, so it's a very weird drawing, but it's called C. And when we write that out, we define it to be Ni equals to nu I, which is our stoichiometric number, and our C here. So that's the proportionality of react. I know it looks like really weird, but I still don't pretend I know how to write it correctly, but a little bit of practice goes a long way. Now, in this process, if you think about it, our coefficient is unitless. Right, so the nu I, that is your stoichiometric number, it doesn't have any coefficient. It doesn't have any unit. The total change of number of mole is in unit of mole. So your proportionality of reactions also have unit of mole. Everything on this page looks like ridiculously complicated, but let's look at an example. It's actually pretty straightforward, all right? So this is an example we have. So let's imagine we have a reaction, which is ammonia goes to nitrogen and hydrogen. And suppose we have initially like 0.8 mole of NH3, 0.7 mole of H2, and 0.4 mole of N2. And we have a final combination of your, we know the final number of mole of hydrogen. And find what is the proportionality of your reaction C, and the number of moles of your other reactant end product. So that's like a Gen Chem question, just complicated by these new terminologies. So let's work on that and see what exactly these new terminologies mean. So we have a reaction, right? So 2NH3 goes to N2 and 3H2. And we know our definition of the proportionality of reaction C equals to delta Ni equals to nu I, that's our coefficient, and this proportionality of reaction. So we have our initial state. This part I'm just rewriting the question here. That equals to 0.8 mole of NH3 and 0.70 mole of H2, 0.40 mole of N2. And we have our final state. So in this case, we have 0.55 more of H2. So in these relationships, we can find out the delta H, number of mole of H2 in this process is negative 0.15 more. So naturally, we can calculate our proportionality of reaction C here equals to delta NH2 over the stoichiometric coefficient of H2. And that gives you negative 0.15 more over its coefficient, which is 3. And that gives you our proportionality to be 0.05 more. So this negative proportionality of your reaction C actually tells you, well, your reaction actually goes backwards. And then from this calculated C, we can calculate our change of mole in N2 equals to C times the coefficient of N2, which is negative 0.05 times 1. So that's negative 0.05 more. And likewise, you can do that for NH3. That's C times number of mole, that's C times the coefficient of NH3, which is 2. And in this case, this 2 here should be negative 2 because that's our reactant. And that gives us 0.10 more. And then you can put in those information here, right? So for NH3, the change of mole is plus 0.1. So we have 0.90 more of NH3. This process, that's negative 0.05. So our final number of mole of N2, that's 0.35. Right. So these are just Gen Chem. It's just like slightly more complicated with the more careful definition of like new things like stoichiometry coefficient or your proportionality of reaction C. All right. And you should be very confident in doing all those calculations just with the new terminology and notation. So what does that tell us? So now we know these new definitions, and let's consider a chemical reaction equilibrium and write out the general form for a chemical reaction equilibrium. So when we're talking about the change of number of mole of some substance in your chemical reaction. All right, so this term is what we care about. That's the change in moles of species I. And in here, we have the stoichiometry coefficient. Let's use a different color. And remember that coefficient is negative for reactant, positive for products. And this one is our infinitesimal change for your proportionality or extent of reaction. So that's the general expression we can write out. Your coefficient remain the same. It doesn't care how much of the reaction takes place. And what we're talking about is building a link between the changing number of mole of a specific species to the overall extension of your reaction, or proportionality of your reaction. And let's take one more step to look at our chemical reaction equilibrium. So at equilibrium, using our same kind of analysis, we need to have this term here to become